All right, in this video, I'm going to explain how to find the domain of a function algebraically using these two examples, algebraically in terms of using the equation, not the graph. So you know how I do it. I'm going to answer the problem first and then go back and explain it more in depth afterwards. All right, busy, gotta go. All right, so when we're finding the domain algebraically, we care about a few things. We care about looking for even roots. For example, square root or fourth root or even roots. And we care about looking at denominators. There's a few more, including real-world context you have to care about. I'll explain that more at the end of the video. And, well, let's get to the point. So, what has to be true about even roots? Even roots have to be non-negative. So a square root, the inside, the radicand, cannot be negative. So we need 4 minus x to be greater than or equal to 0. Could be 0. Then we need denominator to not be non-zero. So simply we're going to write anything in the denominator, any factor in the denominator cannot be 0. X squared plus 1 cannot be 0. So even roots, denominator is not 0. Okay, let's solve it. So how can we make sure the radicand is non-negative? We can make sure x is less than or equal to 4. Oh, my brain froze there for a second. All right, what else? We can't have the denominator to be 0. So solve this, we get x cannot be negative 1. Now what about this? Notice, x squared plus 1 is not equal to 0. X squared plus 1 is never equal to 0. It's always, if you think of the graph, x squared plus 1 is always above the x-axis, and x squared, well, it's never equal to negative 1, so we don't care about that. So the final answer for this is x must be less than or equal to 4. X is not equal to negative 1. You could leave it like that, or you could put it into interval notation, which would be x must be in the interval negative infinity to 1. Negative 1. And then we have a gap there because it cannot be negative 1. And we have negative 1 to 4. That's your final answer. What about this? Well, again, we have a denominator. Denominator must be non-zero. And we have even roots. Even roots must be non-negative. This is not an even root. This is a third root. It doesn't matter. You can have third root of a negative. That's not going to affect our domain. This is an even root. We want this to be greater than or equal to 0. So this one's easy to solve. X cannot be equal to 5. This one, I'll do a little factoring. X minus 2, x plus 2, x squared minus 4 is a difference of 2 squares. How do we make sure that x minus 2 and x plus 2 are greater than or equal to 0? Well, look, we've got two zeros at 2 and negative 2. And if we're to sketch this out, we get an upward parabola. Where is it greater than or equal to 0? Here and here. So to the left of 2 and to the left of negative 2 and to the right of 2. And then we have one more requirement. X cannot be 5. So that's going to affect this interval here. So our final answer is negative infinity to negative 2. 2 to infinity. Oops. I wish I had an eraser. 2 to 5. I really wish I had an eraser here. Really wish I had an eraser here. Wow, I do have an eraser here. That was magical. And then 5 to infinity. Wow, I wish I had a higher quality pencil. Who made this pencil? That's okay. We'll get it better next time. All right, there's your answers. Okay, let's go back and explain a bit. So, for algebraic domains, again, really there's two important things we focus on in Precalculus A. Even roots must be non-negative. They can be 0, but they cannot be negative. You can't take the square root of a negative when we're talking about functions, because functions have real outputs, not imaginary. And the denominators must be non-zero, because you can't divide by 0. There are some other cases, real-world context. I'll talk about some examples later, in other words, word problems. You also, in Precalculus B, would need to talk about trig functions, like you can't have the tangent of some values, and logs. You can't have the logs of anything negative or 0. But for our purposes, Precalculus A, we only care about even roots, like square roots or fourth roots, and denominators. Think about it. How can we make sure this inside is positive? We need something smaller than 4 or equal to 4. If you plug in 4, 4 is in the domain because you get square root of 0. Notice that's why this is a square bracket. And if you plug in something really small like negative 100, you get 4 minus negative 100. That becomes positive. That's good. And then the denominators, you can't have it 0. If you plug in negative 1, you're dividing this whole thing by negative 1. No good. This, however, there's no problem. I actually have a picture of this to explain it. So actually, if you were to plug this into Desmos, you would get something that looks like this. So you notice what we expected. We have a non-removable infinite discontinuity at x equals negative 1. Hence, x equals negative 1 is not in our domain. And everything greater than or equal to 4, there's no values. So it's less than or equal to 4 only. So there you go. That's the domain of this function. And then for the right-hand function, pretty funky, right? The cube root doesn't affect it because odd roots have no domain restrictions. You can take the third root of negative 1. It's just negative 1. It's even roots we have to look out for. That still has to be positive and denominator. So if you look here, we got this weird thing up to negative 2, and then at positive 2, and then 5. Notice all of these are curly brackets. Is that correct? Are all of them supposed to be curly brackets? Uh-oh, I made one mistake here, because actually it could be equal to negative 2. And it could be equal to positive 2 because it could be equal to 0. You can take the square root of something 0. So there's one adjustment there. Since this is greater than or equal to 0, you have square brackets. And this is the funky graph here. Everything up to negative 2. And then starting back at 2 and ending at 5. Okay, that was a long one. Hopefully you don't have to rewatch it too many times to understand it. Remember, look out for even roots, denominators, and as always, go blue.